In this lesson, we're going to be looking at graphing, and I can't emphasize enough to you how important this is. Graphing in physics is never about, I want to draw a graph just for the heck of it. We draw graphs because it allows us to analyze data more meaningfully, and sometimes, in fact, do an analysis that otherwise we couldn't do using the numbers as they were presented to us, or they give us a better answer than we could otherwise get. I have the note here that there are sheets for you, depending on which calculator you have. So you don't need both sheets. You need a sheet for either a TI Nspire or a TI 8384. So in class, these are available to you. On my website, on the Physics 20 Notorific page, there is also links at the very, very top left where you can get those sheets also. So you need to be looking at the one when we get to that stage of how to use your calculator to do this graphing, because it's called a graphing calculator. So why wouldn't we use it to do the analysis of this for us? So first we'll talk about the old way, then we'll talk about the graphing calculator way. When it comes to graphing, you have to have 5 elements on a good graph. You have to have a title, and it must be given as y as a function of x. Whatever you've got on the y-axis as a function of x, that's the way the name has to be given. You don't name the x-axis first and then the y-axis. That's wrong. It also means that honestly, on like even exam questions, when we say to you something like d as a function of t, we're telling you what goes on which axis. That is not a mistake. It's not just meant as sort of a passive, oh yeah, whatever. We're actually giving you a hint then of what has to be on that graph. If I say that it's a graph of d as a function of t, d, the displacement, has to be on the y-axis. T has to be on the x. Use that to get the correct answer, okay, to do the correct graph, I should say. Then we have to label our axes, including units. The x-axis, which is in the title, named second, has to be the manipulated independent variable. To emphasize again, that means it's the variable that we are able to change. Now, sometimes this sounds kind of weird because quite often the manipulated variable is time. We can't change time. No, that's not what we mean. But before I do the experiment, I can make the choice that I'm going to measure it every second at 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. A different person doing the same lab might measure at intervals of 10 seconds, 10, 20, 30, 40, 50. That's why it's the manipulated variable. They made that choice. The responding variable is the one that we don't know what's happening until we do the experiment and see what we get for an answer. So that would be things like the displacement. Because if I'm watching an object, I don't know how far it's going to move at 1 second, 2 seconds, 3 seconds, until I actually do the experiment and observe it. So we put our labels on our axes, and we must include the units. Whether it's on a table of values given to you or on a graph, remember, units are always shown in soft, rounded brackets. That's how we show that what we're talking about there is the units. Then I have to choose a scale. And this is often difficult for people to get like a really good one. You've got to be able to fit all of the data within the space of your graph. And you don't want to scrunch like everything into the corner. You want to use at least about 3/4 of the graphing area. Otherwise, it's not an effective use of your graphing space, and your analysis of that data is also going to be harmed by that. So we don't want that to happen. If you're doing all of this on a graphing calculator, you don't even have to worry about that. The calculator is going to do it all for you. We plot the data, and when we plot the data, this is again not a, well, I hope maybe you did it. No, this is a requirement. You must circle each data point. When we do that, we're really saying 2 things. First of all, that just makes it easier to see the data points, because otherwise they're just little dots on graph paper. But second, it also says there's iffiness in every measurement you ever do. So you're kind of saying that that point could could actually appear anywhere in that circle. Maybe a little bit higher and to the left is where it should actually be, but it's that iffiness in the measurements. And then we draw a line of best fit. For what we're going to be doing here, we're going to be doing stuff where we get straight line, linear relationships. So they're the ones that are easiest to analyze. They give us things like slope, and the slope has meaning. It's not just slope, it has a meaning in our physics that we're doing. Sometimes, like if you're doing an exponential decay, like a half-life, then it'll be a curve. And then that's where kind of that ends for us. But today, we're looking at linear relationships and how we can even linearize data so that we force it to be that linear relationship for us. So here's a old-fashioned graph drawn out with its title, d as a function of t. So d, the displacement, is on the y-axis. T has to be on the x-axis because of the order they were given in. I'm showing the units, meters and seconds, in soft rounded brackets. I have a well-chosen scale so that all of my data spreads out nicely across the whole thing. And when I plotted the data, I put circles around each one, and then I drew a line of best fit through it where I've got a few dots above and a few below, and I'm trying to get the line of best fit to kind of sit in the middle of it. But that is, again, part of one of the problems that we have, is quite often when people get to the next step of, oh, I want to calculate the slope of that line, they just go ahead and they keep using these data points, a couple of them, to do their slope. You can't do that. The data points are not on your line of best fit. And you know what? Even if you have some really boring looking data points, and it looks like the line of best fit is right on top of them, we still can't trust that because they won't perfectly be on it. So, very simply, never, never, never use your data points to calculate your slope. You must choose points from the line of best fit. So you can see I marked off a couple here. Those are their values. The x, y paired coordinates of the blue one over here are 2 and 18. So that's the x and y values. And then for the red, I have 4.2 and 40. So if I'm just going to do this old school, I'm going to do my calculation, I'm going to pull out the slope formula, and different people write it different ways. Some people write rise over run or delta y over delta x. I've expanded it out this way to show that delta y and delta x are really y2 minus y1 over x2 minus x1. And please, never ever write them like this. That's y squared, not the second y value. The placement of numbers and letters and capitals versus lowercase, they all change meaning in physics. So we have to write it this way. So I've got my y values that I'll put in, and it has to be the second y minus the first y. So it's like we're reading left to right. The blue one is the one that I would see first, and then the red one. So this is first, and this is second. So 40 minus 18, those are my two y values. If I'm doing this on a calculator, put brackets around those so order of operations is going to work, divided by my two x values, x2 minus x1. You do all of that work and you'll get a slope of 10 meters per second. And I know that it's meters per second because, well, look at what the slope is. Slope is y divided by x, d divided by t. That's velocity. Even just look at the units. Meters divided by seconds. That has to be the velocity. It just has to be for a dt graph. Here's part of the problem though. Somebody else draws a graph based on the same data, being very careful in everything. Their graph will look a little bit different maybe because they chose a different scale, stuff like that. And especially their line of best fit might not be drawn exactly the same as mine. And then they choose a couple of different data points, which is fine. We just try to keep them, or not data points, points from the line of best fit. But we try to keep them spread apart a little bit and do our slope calculation. But that person will not get the same answer as you did. be hopefully close, but it'll be different. Oh, and I should also mention, sigdig-wise, I'm taking a few liberties here with showing 2 sigdigs. Don't worry about that. I'll show a little bit more about that when I get to the next better example. But my whole point is that slopes done this way are questionable at best. Different people legitimately, in a fair way, will get slightly different answers. So this is not the best way for us to do it now that we're in Physics 20 or Physics 30. Doesn't mean this is wrong though. And if you're ever in doubt, you can fall back to doing things this way. In fact, that is exactly what I'd suggest you do. Don't just give up on a problem. Go old school on it. Anytime I give any quizzes or exams and I'm doing something with a graph, I honestly give the big old empty graph place like this and a space for you to do your old-fashioned slope calculations if you choose. But what I really hope is you're going to use the calculator method because of its superiority, and that once you get good at it, it is so much faster, so much more accurate, just better in every way, that you'll do that. And so on questions involving graphs, I give the graph area and say, oh yeah, go ahead and do your calculations if you want. Or I ask you to give the values of the slope and y-intercept from your calculator. I'll have just a little box off to the side that says m equals, b equals, because that's what they're called on your calculator, and I just want the unrounded values there, because if you can show me those, that is proof that you must have done it correctly on your calculator. And then this is just blank. I'm not seeing you draw anything. It's one method or the other, not both methods. So when it gets to using a TI Nspire or an 8384, we are getting the best possible answer that we can get. Your calculator can use all sorts of algorithms to generate essentially mathematically perfect values for slope and y-intercept, the best that we could ever hope for. This is what you're going to be doing anytime you do any labs. It's also what you're going to be doing into Physics 30, like the whole way through. This is the expected standard that we want you to be going at. So I'm going to show you an example, and it's going to be a little bit weird, but we're going to try to apply a set of rules to it called line straightening. And it's exactly what it sounds like. We're going to take a line that otherwise wouldn't necessarily be straight, it would be exponential, and we're going to make it a straight line so that we can get a valuable value for like a slope or something like that. Sometimes line straightening is also called an averaging technique, and that can be a bit misleading. I get it. Because when you hear averaging, you think, oh, I'm going to add 5 numbers together and divide by 5. That is not what we are doing here. No, not at all. Instead, averaging just means looking at all the data as a whole and getting, on average, what is it telling us is the trend in the data. That's why it's still line of best fit sort of stuff. So, when you are doing this, and you're using data that would typically have given you a curved line, and you're going to straighten it so that it gives you a straight line, we don't just willy-nilly change the numbers. Instead, we need to identify the main formula that is the physics formula behind the problem or the experiment or whatever. At the Physics 20 level, we basically usually just give that to you. At Physics 30 level, we expect you to realize, hey, that's the only relationship from the data sheet that could work for this sort of experiment. Then, this part sounds weird, we get rid of the extra variables in the formula, the things that are not the manipulated and responding variables. That does change our relationship. It's no longer going to be a formula with an equal sign. It's going to be a relationship with the letter alpha, meaning that we're looking at how things relate to each other. That's all. We look for something that's exponential, something that's being squared or cubed or square rooted or something like that. And great, once we've identified that, whatever variable is being squared, come up with a new column of values that shows those being squared. Plot that information That will give you a straight line graph. And then we can relate that back to the original physics formula so that the slope actually truly means something to us. Now, a lot of this, trust me, I know it's going to seem very like, what? Until you actually see a problem and we work through it. That's exactly what I'm going to do now. And then what I would suggest is you work back through the problem yourself, especially practicing the skill of getting it into your calculator. And that's going to be what allows you to be more successful with these questions. And you do have to practice them a few times. There will be other examples throughout the course of doing this. So it's going to be something that you do have more and more and more practice at doing. So the question that I'm describing is where we have a student performing an experiment to measure how centripetal force changes as the velocity is altered. Now, I don't expect you to know right now what centripetal force is. That's okay, don't worry about that. I'm going to give you the formula and everything like that, so don't worry about that part. Now you see in red, I say, using a suitable averaging technique. What? That's your cue that you're going to be doing a linear regression. You're going to be doing a graph. It might not sound like it, but that's what you're doing. And then I actually try to help you. I say that as you're going through that process, you'll have to determine a new set of values that, if graphed, would give a linear graph. We're going to see how we do that. We're going to identify the meaning of that slope. And no, I don't mean just, oh, slope is rise over run. How does the slope relate to the physics formula? And then we're going to use that to determine the mass of the object if it's going through a circle that has a radius of 1.15 meters. So here's my original data. The centripetal force measured in newtons and the velocity measured in meters per second. Notice that because this is a chart, a table of values, we are showing the units in rounded brackets. This is a requirement, okay? I've got my values for centripetal force and velocity. To make any sense of this, I need to know the formula that I'm using. And it's this one. Centripetal force equals mass times velocity squared divided by radius. Okay, nothing too crazy there, right? I'm not saying that you've necessarily done that formula, but it is just another physics formula. Now, looking at the information that was given to us in our data table, what I identify is that between the centripetal force and the velocity, those are the only things I've been given. One of them must be the manipulated variable, and one of them must be the responding variable. It means that when I look over at the formula itself, the mass and the radius, which were not given in my table of values, must be controlled variables. Those are the ones that I kind of toss away for a little while. Now that's dangerous. It's not going to be a formula anymore, but I can move them kind of out of this and I can get a relationship. Centripetal force varies as v squared. So all I did is I'm scratching out the m and the r. Fc would then be related to just v squared. Hey, one of those is being squared, the velocities. So that means I should come up with a third column that shows velocities squared, because that's what my relationship shows. Now, really what this means is, honestly, just taking every one of those velocities and squaring them. So I would get a column that looks like this. Velocity squared, notice the units, still in rounded brackets, are shown as meters squared per second squared. So they had to get squared also. And then all the numbers got squared. These numbers aren't so bad, and there's not many of them, so I could do that quickly. But what I want to show you is how we could do this on an Nspire, and then later a TI 384 calculator, so that, especially if we have lots of numbers, this just all happens auto-magically for us, and then will give us those necessary slope and y-intercept values. So, here's the Nspire setup. If you start on home, which is where you should begin for these, we do need to create a new document. So you would choose number 1, new. Now this can be a bit misleading because people often want to jump to this one, graphs. Wrong. That's when you're doing mathematical functions and that's not what we're doing in physics. So we're not using graph. Instead, we go all the way to here, lists and spreadsheets, because we want to create a spreadsheet. And if you've ever played around with stuff on a spreadsheet like Excel or Google Sheets, this kind of looks familiar to you. I'm going to take those numbers that I had previously given you and I'm going to put them in here. Now I am going to label these columns. I must do this for all of this to work nicely. And so the first column is centripetal force, and I'm going to type it like that. I'm not going to say anything about units, it's not that fancy, but I just type FC for centripetal force. You'll notice that I can't actually do much for formatting here. Don't worry about doing capitals and don't worry about doing subscripts. As long as you can look at that and go, oh yeah, it's centripetal force, you're good. Move over to the next column, call it V for velocity, and again, we're golden. That's all we need. Now I'm going to go down and I'm going to start typing into these down these two columns, the values that were given to me. Now these are the ones that I had just shown on that previous slide. So I'm not just getting them from nowhere. They are the numbers that were given to me. And I'm just typing them in, basically reproducing what was already in the chart of values that was given to me. So I've got those for my forces. And now I'll put in the values, oops, for my velocities, like that. Now remember, I need a third column that is the velocities squared. And sure, again, like I could go through and just calculate those. Let the spreadsheet do the work for you. I'm going to make a new column here, and I'm going to call it VSQ, velocity squared. Again, I can't use fancy notations or anything. I look at that, and to me that means velocity squared. I have to give it a different name. That's good enough for me. You can call it whatever you want, as long as to you it means velocity squared. Now I go one box down, and you'll see this row has an equal sign way over here. It's saying, tell me what you want me to do, and I'll do the calculations for you. So on the keyboard, I have to hit this equals button that's next to the trig button. So I hit that, and notice it's saying, oh, so you want to make V squared, this column, VSQ, equal to something. Okay, what do you want me to do? I then hit this button just above the 9 on the keyboard that says var for variable. And it brings up this. It lists all three of the names I've given these columns, FC, V, and V squared. I want to take the information that's in my V column, and way over here, I'll hit the X squared button. I want to square them. Hit enter. It does all the calculations for you. And it even means that if at some point you realize one of your numbers was wrong and you needed to change it, it will make the change to the V squared for you. If the numbers are big and ugly or you have a lot of them, this is really helpful because it means you don't have to go back and recalculate things. You can just fix what you need to fix and then it takes care of it for you. Now these are the values that I need to use, and I do promise you that because I have now calculated V squared, I'm not going to be using the V column again. That one's kind of dead to me, okay? I'm just using the centripetal force and the V squared values. I'm also going to give you a little bit of extra help. I'm going to tell you that if I was doing this as a graph, I need it to be centripetal force as a function of velocity squared. I'm giving that to you. That means centripetal force, since it was named first, is on the y-axis, and V squared has to be on the x-axis. Okay, well, let's get a graph for this. I'm going to add a page. So I hit the control button, and then the dot button, which you'll see has plus page above it. Now again, I'm going to make a graph out of this, but I'm not going to choose number 2 graphs, because that's still mathematical functions. I'm going to choose data and statistics. And it gives me this, which I know looks like a bit of a mess. And on your calculator, if you're following along, the dots will be in different places. That's because I haven't identified yet what the axes are. So use your pad to scroll kind of over to here and click on that one. Tell it to make that centripetal force. Now we go down to the bottom, click on it, and choose it not as V, but as V squared, which if I did choose V, you notice how that has overall sort of a bit of a curve to it? That's not a linearized graph, that's exponential. I can go back and I can fix it if I need to by just clicking on it and choosing what I need. And there we go, nice linear relationship. But where is my line of best fit? How do I get that slope and y-intercept value that I need? It's the menu button. Menu is like magic for us. It does all the analysis stuff that we need. So I click on menu, and from all of these choices, you can go through them, and if you see something, you know, oh, that's wrong, you just hit the escape key to go back if you need to. But eventually you get down here to where it says analyze. Choose analyze, and then number 6, regression. You see at the very top there, as soon as you go on to regression, the first choice is show linear mx plus b. That's the standard way that we think of a straight line in math. That's the one we choose. And there it is. Y equals 20x plus 0. Remember, that is in the format of y equals mx plus b. So m is 20 and the y-intercept is 0. Those numbers sometimes can be shown with lots of extra digits and stuff like that, and that's okay. Now, if I do need to do any calculations with those numbers, I can add another page, so Control plus page, add a calculator page. Now, I'm just making this up right now, but let's say for some reason I want to take my slope and multiply it by 5. Okay. 5 times. Now, don't necessarily go back and read your number, because especially if it's a number with a lot of digits, you might not copy it over right. Go to the var button again. That's variables that have been generated by you and the calculator. Click the var button for variables, and you'll see all these choices show up, and most of them you never have to worry about. But you see this one's called stat m. That's the statistically calculated value for m, your slope. Hit it, and it substitutes in whatever was from your previous slide. Look at that, 5 times 20 is 100, because it used the value for slope. So we can use that if we need to for doing calculations. I'm not saying it has anything to do with our analysis here for this one, but just so you know that you can hit those buttons if you need to. So now let's look at how we would do this on a TID3 or TID4 calculator. It's going to look a little different, and it's not nearly as forgiving for you being able to change things or enter things, stuff like that. First thing we're going to do is click the stat button. And from this screen, we want to choose number 1, edit, because we're going to put in our list of values here. Now, it's very important to understand that the L1 and L2 columns have to be the ones we're entering. If you see stuff like it starts at L5 or something, you have to basically do a reset on your calculator. It's the only way to get it to this, which is what we need. L1 has to be your X values, your finished X values. L2 has to be your Y values. It has to be what you actually want to graph. So I'm not going to get it to do all those fancy tricks where it'll calculate things for me necessarily and stuff. Usually what I'll do is off to the side, I'll do those calculations myself. So I know that this was 1 squared, and this was 2 squared, and 3 squared, and 4 squared, and 5 squared. So those are the numbers that I'm going to put in. Those are my X values because V squared is on the X axis. L2s, they have to be the values for my Y axis, the centripetal forces. So I type those numbers in. Now this is quick on here because of the way that I can put in the values. But remember, I can't, other than doing a quick little back check like that, I can't do some fancy stuff with this, and I can't check my regressions the same way. But now what I'll do, now that I have those values, is I'll hit the stat button again, and I'll choose Calc And this one, number 4, linear regression, linreg, ax plus b. Back in the 1990s, when TI 83s first came out, and TI 84s still have the same basic programming in the background, they decided at Texas Instruments not to write mx plus b, but ax plus b. That actually means something different in math, really, but we got to kind of roll with it. A on these calculators means the slope, and b is still the y-intercept. So choose number 4, and it'll come up with something that looks like this. Depending on the software on your calculator, it might look a little different. Don't worry about that. Just go with it. Use what it's given to you. Just hit enter a few times until you get to here. Click calculate. Your calculator might stutter for a second as it calculates it, but all you really want to do is get it to here where it shows you a value for your slope and y-intercept. Now, a lot of times these are going to be lots of numbers written down, lots of digits. Write it all down, okay? Just scribble it out on a piece of scrap paper. This one's at least easy, 20 and 0, okay? No biggie. Whichever method I used, though, I got the same formula. Y equals mx plus b, y equals 20x plus 0. So whichever calculator I used, I'm still getting the correct values for my slope and y-intercept. If I was doing this on a calculator, instead of doing an old-fashioned graph, these are the two numbers that I would write down, saying my slope is 20, my y-intercept is 0. Now, especially if those have all sorts of extra digits, that's totally fine. I now have the numbers that I need to do my calculations. The important part here is, for me, getting that slope. It has meaning, because I know that slope is really y over x. My y-axis is centripetal force. My x-axis is velocity squared. That's what I need. I need to know that this is my y and this is my x-axis. That means the slope is really equal to this stuff. But I can take my original formula and I can manipulate it to get fc over v squared, because it means dividing this side by v squared divides this side by v squared also then, so that I get something that looks like this. The nifty part is, if slope equals centripetal force over v squared, and centripetal force over v squared also equals m over r, I can just put those together. Slope equals mr, because they're both equal to the same thing, fc over v squared. Now, I can take the formula. I know the radius because they gave it to me. I have the slope. It's just a number I calculated. And I can find the mass. And I'm sorry, I know mass, slope, m in the formula from your calculator look like the same thing. That's why I wrote the word slope here. I manipulate the formula. This is where it's good if you're on an Nspire and you have that value for 20. You can just, var, stick it in. 20 times the radius that was given to me back in the question gives me a mass of 23 kilograms. And this has 2 sig digs, because when we look back at our original numbers, all of the velocities only had 2 sig digs. So I should round off to 2 sig digs. And that gives me my final answer, a mass of 23 kilograms. The best possible answer from my data of the mass of the object. Practice this a few times, try some other questions, and you will get better at this. You gotta get good at the skill of handling the formulas and the skill of doing it on your calculator.